little deeper into that and try to make sense of it. And okay, so here I'll talk about these two modules have evolved currently, the macroscopic versus microscopic properties and how these things are connected, and then we'll get on to the typical mode of thermodynamics education, which is the talking about systems and variables and all that. Okay, now the whole idea of thermodynamics, if you will, came from a macroscopic point of view. And what do I mean by macroscopic point of view? The idea that the thermodynamics was felt as if it was a phenomenological development. You know, people didn't start from atoms and molecules when they talked about thermodynamics. It was a movement. It was an sort of an approach to understand what is happening in materials by observing what is happening on a bigger scale. You know, bigger scale. What do I mean by bigger scale? It's by the scale with which we realize stuff. For example, as a human being, we perceive certain changes. Okay, that is within the reach of our sensory perception. And sensory perception means touch and feel and eyes, and then other ways of feeling it. That there is some change happening in the system. All right, and from those things, the idea came of the idea about a thermodynamic behavior came about, right? And that was not until very late that people started looking at it in a very minutely, very microscopically. Okay, so that's what I'm saying. When the macroscopic point of view is that it's a large scale thing. It's identifiable by some perceived changes that we perceive from our sensory perceptions, and it sort of gives you a macroscopic definition of stuff. Like talk about thermodynamic quantities or coordinates called volume, or a pressure or a temperature, or what is there in the material, which is called composition. And these things don't have to be defined in a very fine way. You understand that when you take a bottle of air or a bottle of liquid, and if the volume of the bottle of the liquid changes, you understand, you can see it. Okay, now you take some air inside a balloon, and then you want to increase the pressure, and the way you increase the pressure and what happens after the increase the pressure, you can actually understand it, you can feel it. So that's that's within the domain of sensory perception, macroscopic, bigger things, bulk things, macro things, that you understand. That's sometimes I call it the engineer's approach, right? And it might not be written in any book, but I hope I make my an approach clear to you. Engineers work with bulk things. They do a gross estimation of substances, and then they are always right. So I would like to say that the development of thermodynamics as a field of science has started actually the engineer's way. By observing things what's happening on a gross scale, on a bulk scale, right? And it is much more phenomenological. Phenomenological meaning that things happening as a phenomena, you observe that, you try to understand what's happening there, that, and then you develop theories for that. So that's a phenomenological development. And these are, if you look at the history of science, whatever has happened, some things have happened at a very fundamental level. It's like bottom up approach, and some things have happened in a very gross level. It's like a top down approach. You understand you see something is happening, and you try to delve deeper into that, and you find many subtle and very finer things which are otherwise not perceived nor measured by in a bulk scale. All right, so that's the macroscopic idea of things. But then as the developments happen in the thermodynamic domain, then people also realize that it's actually can connect to microscopic substances. It's just that's the bottom up approach. And in a microscopic point of view, you look at what is happening in the atoms and the molecules level. right? Now, and when you go deep into that, the way the energy of a system, or a packet of gas, or something that is defined, is it's an average estimation of uh, each and every atoms and molecules. Their energies summed together gives you the average property. Like for example, the average measurement of the rate of change of linear momentum due to molecular collisions that happens in a unit area, for example, that we call pressure. In gross scale, we are simply measuring the pressure. But in the microscopic scale or the molecular level, if you go back to your 10 plus 2 studies, you've heard something about the kinetic molecular theory or kinetic theory of gases, where it is a very simplified model that in a gaseous environment that, molecules we call like a spherical balls, and then they sort of, they undergo elastic collisions, and then they come back, they're always in a state of motion, and then there's a sort of time scale and the distance between, between the collisions, and then accordingly you formulate, the state of that gaseous system. So that you take different properties of that, you can calculate something called a pressure, something called a volume, something called temperature, and all that. But that's in a very individual states. All of those states put together, that gives you the property of pressure or volume or something. That's a microscopic viewpoint. That's the molecular viewpoint. Okay, which is exactly opposite to what we talked about in the last slide as a macroscopic point of view. And this microscopic point of view was greatly helped by the Boltzmann distribution, Ludwig Boltzmann distribution. It just stays. It tells you that there are certain energy levels, and each and every energy level will be occupied by some number of atoms and molecules of the particles, right? And you raise the temperature, it's more likely that higher energy levels will be occupied by these atoms and molecules. So that distribution is called the Boltzmann distribution. And here in the next slide, I've made a graphic taken from um, Paul and Atkins' book for physical chemistry. So here, he clearly says that the energy levels of molecule and atom is quantized. I think you know that. And if there is any temperature other than zero, other than T is absolute zero, all of those atoms and molecules, their energy will be distribution over a range which is like an allowed range of energies. Now, the energy of if the energy of the state is much higher, then the probability that there'll be more atoms and molecules is low. You don't actually fill molecules immediately with higher energies. But again, when temperature goes up, okay, when the temperature is up, then there is more likelihood that a higher energy state would be occupied. That's the distribution. If you look at the slide on the right, then it talks about the. Okay, do you see the cursor moving? All right.
Yes,
See
sir.
on the left, there's a population of atoms and molecules over the certain amount of energies. But then when the temperature goes up, and here let's say it is a little lower temperature, this this is a higher temperature, and this is where the energy goes up. But here, if you look at it in the lower temperature, most of the energy levels are not filled. But if you go to high temperature, all of these energy levels are gradually filled, and you see that gradually, more and more higher energy levels are filled. But then the population there is slightly low. So as it says, if the temperature is higher, temperature is going up, then it's likely that a higher energy state will be occupied. So that's the distribution. So in a low temperature distribution is like this, and at high temperature distribution tapers to or it sort of extends to higher energy levels. So that's how the energy of the particles could be distributed in a temperature range depending on here we're talking about absolute temperature, of course. But then, so it's very important that we need to understand there's a connect between macroscopic properties and microscopic property. I think that's the beauty of something, something profoundly true, profoundly strong theories, that even if you come from both directions and when you meet, there's nothing like it. Both are right. So you from the way you look at it from microscopic point of view, it's right, and the way you look at it from the bulk point of view, that's also right. That's the connect is there between Boltzmann constant, the KB, and the very common universal gas constant, which is R. Okay, and this is connected by the Avogadro number. It's a very simple equation, but most of the people forget about that, and I think we kind of screw up a lot of things by misusing or not using properly this equation. So it says that there's a connect between this universal gas constant and Boltzmann constant. If you multiply the Boltzmann constant with Avogadro's number, it sort of simply gives you the universal gas constant. And if you look at it, when we talk about pressures, volumes, and temperatures, and the universal gas constant, the combined gas law, we lot of times use R. Okay, R is something, it's very engineering approach, very bulk gross approach, but then you only use K in only molecular terms. That's the connect. We are pretty much looking at the same properties using R as you would be doing with K. Just that when you talk about K, like you divert your attentions to levels which are extremely fine. Whenever we are using Boltzmann constant, then you should be thinking, you should be looking about atoms and molecules. Whenever we are talking about R, the universal gas constant, then we are talking about an ensemble of things. It's like a bigger bulk, volume, a macro kind of properties. When you talk about KB, we're talking about individual atoms. And that's one of the reasons that you simply Avogadro's number is that's the magic number which kind of connects the mole of substances to individual substances. More on that when we kind of go into gaseous states and things like that. Right? So that's it. R is NaK, and just one more thing which is of importance when we do calculations and all that. When you use R, you always make sure that you get things in joules, kilojoules, and things like that, right? But when you use K or KB, either way you call it, you would get things in electron volts. That's the energy unit that you're using. But when you talk about R, use the joules, kilojoules, megajoules, whatever. But when you talk about K, always use electron volts and things like that. Because that gives you the perspective of being working on a micro level vis-a-vis working on a macro level. Right? Okay. Now we come to the second point. Okay, do you want to stop for a while? Want to discuss sort of stuff?
No, sir, it's fine.
It's fine then. Okay. Okay. Now we so that's the group or basic ideas that we kind of covered with regards to um, how to look at thermodynamics from the microscopic point of view versus microscopic point of view. And now let's get into some of the basic general terms used in say thermodynamics. Talk about systems and coordinates and thermodynamic quantities, thermodynamic parameters. Some of these are similar, some of these are slightly different. And let's just for the sake of simplicity, let's go through that once again. So system, with any thermodynamic system, okay, so it's when you look at a collection of matter, you choose it separately from the rest of the surrounding, and okay, and then it is sort of bounded by a surface, which is typically an imaginary surface. Sometimes you can see well-defined surfaces, sometimes you don't see well-defined surfaces. But then let's say you isolate a set of matter, and then there is some kind of boundary, and then there's something beyond the boundary. Okay, so that thing, that is a system, that is a thing of interest. There's no hard and fast definition as such for what would you call a system. A system is in my language, my thing of interest. I'm interested in this bottle of water. What's happening there. If I put something, if I take something out, that is my thermodynamic system. I want to understand what is happening in this thing for, with the influence of X and Y and Z and Z. That is what I want to understand, right? So that the thing that I want to understand is my system, in a gross language, if I may put it. Right. And of course, there's a surrounding meaning something that is beyond the system, which may or may not have an influence. So yeah, please switch off your microphone if anyone is there. Please switch off your microphones so that it's not difficult for others. If you want to ask a question, switch on your microphone and then ask a question. Okay, so you have a system and you have a surrounding, and anything that is that is separating between the surrounding and the system is called a boundary. So it's nothing great, or just we have some kind of definition so that we sort of isolate our interest, and then so that we just only concern about what is happening inside our frame of interest. And there are so many examples you could find in anything that like water bottle, or an air canister, or some kind of a gaseous reactor with ethanol, methanol, or some other gases and all that, a battery, electrochemical cell, you have talked about a soap bubble. All of those things can be called a thermodynamic system. And if you carefully work on that, you can see a lot of changes that other thermodynamic properties can bring onto that system. Okay. And all of these systems are defined by a set of thermodynamic coordinates, which, in a way you could say the thermodynamic variables, things that influence the system, influence the stability of the system. All of these terms, I don't know which term is to be spoken first, because there's so many common terms, and I think we, in a way, know most of them. So it doesn't matter. We start with the simple definitions and all that, and as we go on to a new term, we'll try and understand, right? And then when you talk about a system, then you have different types of systems. You have open system, closed system, and isolated system. And if you look at it, it's simply related to. Let me just take it out here. Okay, it's simply related to the way matter and energy interact with the system, interact with our frame of interest. When you can put energy inside the system and also mass inside the system, then we call it an open system. It's taking everything, and it's an open system. That sometimes we study those systems as well. Okay, and when we talk about a system where you can put energy in, but then you cannot do mass transfer, that will be called a closed system. Not typically a closed system, and closed for mass, but energy can be put in. All right. And the third category would be an isolated system, where neither the mass nor the energy sort of goes in, which is what is being depicted in the side cartoon. So what are the examples of this open system and closed system and isolated system? And let me tell you one thing here is that isolated system is actually not of interest to us, kind of not so sort of useful for thermodynamic studies and all that, because it neither takes energy, nor it takes mass, so it's useless. For example, if you look at what is happening in Mars, the whole Mars would be a system for us. It is something which we can put mass in there, neither we can put energy in there, so that would be an isolated system for us. Okay, but then if some talk about extraterrestrially, sun can put energy into the Mars system, or the Mars planet, and I don't know if there is some other things happen. So that's on a there again, that's a scale changes, and then all those things change. So I want to say that isolated system is uh, largely of no use to us, so shouldn't bother too much about it. But talk about open system and closed system, and I think a lot of people would have given you an example of what open systems are and what closed systems are. So let me, if I take, if I take this bottle of water, and this, let's say, if I say it's a glass of water, when things are open and all that, I can put water in, and that would be called an open system. All right. I can put water in, that means I can put mass in there, and I can put energy into this, because if I heat it up, although it's kind of a excuse me, it's typically an insulating container, but then if you convert this, if you take a glass one, glass is insulating, but then it's still heat it up with heat up with it. So that way, by putting a flame beneath, you can heat it up, and that will be an open system. And if I close it, very physically, very literally, if I close it, this becomes a closed system. So I don't know, somebody probably wrote it like that. That's why this was called closed system. I just put the cap in, and I cannot put more water into it unless I open it. All right, but can I put energy inside? Yes, I think I can put energy. Several ways I can put energy in. Like if I have to put energy, I can shine a laser source. That actually would put energy into the system. I take this bottle and then keep it in the sunshine, under the sun. Energy goes into the system. I shake it up. I'm putting a lot of energy into it. I simply heat it with a flame. I'm putting a lot of energy into it. So it is kind of a closed system. It's not taking mass, but by many routes you can actually put energy into it. And these are these open systems and closed systems. These are actually of very lot of interest to us. All right. So isolated system is not so useful, but open and closed systems are extremely useful for us. Okay, now, okay, we have been talking about these properties, thermodynamic properties and thermodynamic parameters, thermodynamic coordinates. We'll talk about why would we call it coordinates at one point. But then let's say these are, of course, variables. And variables, what is variable? Variable meaning if these are the things which actually define a thermodynamic system. Okay, these are the attributes which define a thermodynamic system. For example, if I have to define you, or how does the government profile us, saying that this is person of this height, person of this weight, brown eyes, dark hair, and things like that. These are some of the attributes, right? Now, trying to identify you. It's a bad example to give you, when talking about thermodynamics. But then I think, we should be able to relate thermodynamic things with very abstract concepts, things that are not possibly related to us, directly, and then take inspiration from that. That's why I'm saying it. So there are thermodynamic properties when fixed, when you sort of pinpoint them, they actually characterize a system. Okay, I mean, it could be simply a water bottle or a chemical reactor or a solid substance in a certain temperature and solid substance of certain compositions and all that. Okay, now these thermodynamic variables, uh, mm, if they are put on some kind of a graphical representation, right, then you call them thermodynamic coordinates. Right? If it's simply about defining it, you call it thermodynamic variables, thermodynamic parameters. Okay. You want to change it, like if I do something or modify something and something else happens, then I would call it thermodynamic variables, because these are variables. These parameters change. Okay, that's why I call it thermodynamic variable. And if I, as I said, if I have to plot the state of that system in some kind of a thermodynamic map, right? Then I would call these thermodynamic variables as thermodynamic coordinates. It's as simple as that. So thermodynamic parameters, thermodynamic quantities, thermodynamic variables, thermodynamic coordinates, they mean almost the same. There are not major differences in that, right? Now, but it's very important for us to identify two sets of these thermodynamic variables or thermodynamic properties, which are extremely different, and we need to, we can actually make a lot of sort of mileage out of it, right? One is a set of intensive properties. The other set is called the extensive properties. I've directly written it here. Okay. The intensive properties are something which actually don't really matter as to how much of material you have. Right? And the other one would actually change with, if you put more in the system, if you take more of that material, then that property that we are talking about would change, would increase or decrease depending on the amount of matter. All right. Now, this is a very tricky tricky parameter. Not so tricky, but then you'll have to put your mind. Let's say if I take let's say volume. This is thermodynamic system. I have this much of volume, right? Now, if I put if I remove the cap and put more volume on it, all right? So I added more amount of matter into the system. Now, what is changing? Does volume change? Yes, it was this much volume, and I added this much more volume, so it became more volume into. So volume is the parameter which actually depends on the amount of matter that is being dumped in here, or that's being used. Okay, so volume in a way would be an extensive property, right? But let's say, what about pressure? What about pressure? The pressure is, if this bottle of water, open at one end, or even if you close it, it doesn't really matter. If you put more water into it, the pressure acting on the water, does it change? Not quite. Okay, if you take out water from here, so does it change the pressure in the system? Not at all. So in that sense, pressure is actually not influenced by the amount of water that you have in the system. That's why pressure would be an intensive property. Likewise, if you do a measurement of this temperature measurement of this water, add more water into it, would the temperature change? Of course, you'll have to excuse or neglect that, if I put more water, water will be disturbed, and then, that might influence a change in temperature. Let's say in an ideal system, I do it very swiftly, transfer another 100 ml of water into the bottle. Would the temperature of the system change? Perhaps no. Would the density of water change? Perhaps no. Would the refractive index of the system change? No. So these are the parameters which are actually not dependent on the amount of material that you put in. All right. So they are typically to be termed as intensive properties. On the contrary, talk about something like energy. Okay. Now, if energy meaning, let's say the energy content that is derived from this much of water. All right. Now, if I put more water into the system, the amount of energy that is available to me is higher. That means the amount of energy that is available to me is actually a function of the amount of matter that is there. Now, that's got to be an extensive property. Now, talk about the heat capacity. Unless you talk about something like a molar heat capacity or some specific heat capacity or something, talk about heat capacity. Heat capacity is some form of energy gain. It depends on the amount of material you have. You have some number of per gram, and then you have 100 grams of it. You have more heat. Okay. You added another 100 grams. You add more heat into the system. Heat capacity of the system is higher. Like that, What about mass? I have I have a 500 ml of water here. There is some mass to it, all right, and I add another 200 ml of water. What happens to the mass? Mass would change, and that's why mass is again an extensive property. And let's say instead of this powder, this liquid, I take some sort of powder, a bulk powder. For example, आपका ले लीजिए, आपका talcum powder ले लीजिए. You take this much of talcum powder and you add again another this much of talcum powder. So what is the available surface area? If you grossly look at the available surface area, that actually increases, right? So again, the surface, if you talk about surface area as such, that is a function of the amount of material that you have. So these are the examples of separations in that what would you call intensive properties and what would you call extensive properties. But then if you look at it, all of those extensive properties that I've listed here, it's very randomly listed. There is absolutely no sort of no serialization, proper serialization of it. Although you know that on the left, on the intensive properties, you have these properties. These are fine. Some of these things actually can be connected to the extensive properties thing. We talked about volume, we talked about mass here, and we talked about density on the other side. All right. So what is it? There's some connect is there, isn't it? Think about it. Now we have volume, which is an extensive property. We have density, which is an intensive property. Now you know that when I add more volume, the volume changes, and that's why it is an extensive property, but the density doesn't change. Density of water keeps the same, and that's why it's an intensive property. So you got to do something by which volume can be converted to density. Here, that's an example of volume versus density, but then perhaps there is a connect in the sense that all extensive properties actually, if properly normalized, can become an intensive property. And volume is an example. Now, if you take the volume and you normalize the volume with what? Mass. Or the ulta. You take mass, normalize with volume. Mass per volume is density, that's gram per cc. Alright? So volume per mass and mass per volume, there, that's the number that's not going to change. And that becomes the normalization. But when we talk directly about density, just take mass and normalize it, volume, and that no matter how much of things that you put in, that's not going to change. Likewise, we sort of talked about what's the surface area of a bunch of, or it's a sort of a collection of powders, and then that surface area changes when you put another heap of powders onto that collection. But then if you do the analysis called or the quantity called specific surface area, when you use that term, you should be aware that when you use this term specific, it actually normalizes it with either the amount of mass or the amount of volume. All right. We'll talk about surface area, and then it actually changes with the amount of powder that you have. You have more powder, you have more available surface area. I hope you understand what do I mean by surface area of powders. Right? The powders is a small collection of particles, and then the exposure to surface area of the particle is actually taken into consideration when you talk about available surface area. That's very, very important in powder sciences, in catalysis, in every lot of other fields. So powder has a lot of surface area vis-a-vis a bulk made of that powders. But studying powders is also very, very important. The point I'm coming at is that you have more powders, you have more surface area. But then when you do a calculation or you do a quantification of a term called specific surface area, right? That actually, what it does is it takes the surface area and it normalizes it with the amount of mass that you've taken, right? Now you have 100 meters square per gram. If a powder that I'm taking, some kind of an alumina, okay, it's very reactive alumina, let's say, that's an example, and that's useful in chemical industries, and I need to identify that. I cannot identify it as like a bag of powders giving you 1,000 meters square. No, because that will be wrong. Because you have two bags or half a bag, that surface area would be different. So that's why what we do is we normalize whatever the available surface area, we normalize it with the mass either. So that's generally called meter square per gram. That's the unit. Now, if meter square per gram is the unit, then it doesn't really matter. You have 10 grams of samples or 100 grams of sample or 10 kilos of samples. So that becomes a standard parameter. That's kind of an intensive property. So surface area, available surface area is an extensive property. But then talk about specific surface area, that's an intensive property. Likewise, heat capacity is an extensive property, but specific heat capacity, molar specific heat capacity, those are intensive properties. All right. So, and you talk about energy. Energy is an extensive property. When you talk about molar energy, molar enthalpy, or anything, then it becomes intensive properties. I think we should understand this much that an extensive property with proper modification can be made an intensive property, right? I think this should be good for the first class. Now let's stop and then take some questions if you have. Right? I've been constantly talking without an update from you. So let's see if I can take some questions. Right? I'm stopping the recording and right? Okay. Stop recording.